في رمضان يحلو الحديث عن الطعام. تعالوا لنتعرف على أكثر الأكلات الرمضانية انتشاراً، فوائدها، مضارها، وكيف يمكن إعدادها بطريقة أفضل. تقارير خاصة مع سارة الدندراوي يومياً على شاشة العربية.
From the very beginning of human history, new ideas have been inspired by the potent combination of curiosity and observation. In today's technological world, everything you touch, use, see, or do, from striking a match to sailing, railing, emailing, flying, cutting, drying, tying, threading, sledding, trucking, chucking, plucking, timing, climbing, rhyming, typing, swiping, piping, wiping, tracking, cracking, jacking, texting, requesting, talking, walking, chalking, or watching this show is possible because someone, somewhere, observed, experimented, and transformed what was once just an idea into a useful and powerful tool. As incredible as these innovations and inventions are, they may soon pale next to what these explorers, past and present, have discovered and are uncovering. By peering into and probing the depths of the most powerful, tiny, and weird universe imaginable. The quantum universe, a paradoxical realm of seemingly unlimited potential, where fascinating phenomena are being harnessed and developed into new technologies that may alter the world as you know it. Journey into this weird and progressively wired world with the Quantum Tamers. Humanity's first inkling of the quantum universe begins in 1900 with one Max Planck, a brilliant physicist who was trying to figure out why objects changed color as they got hotter. But wait a minute, we're getting ahead of ourselves. Before we get to quantum physics, we need to know a little about classical physics. First, there was this famous guy named Newton, who with a few simple mathematical equations, described and predicted the motion of the planets. This was a powerful idea.
Isaac Newton understood the power of mathematics. He understood that not only we can encapsulate a bunch of facts or data into a simple equation, but that we could use this simple equation to predict the future. What he discovered is that the world is fundamentally predictable.
Next, a gentleman named James Clerk Maxwell showed that electricity and magnetism could also be summarized with just a few mathematical equations.
Maxwell's equations had a tremendous impact on the technological development of last century, the 20th century. Everything we see around us, TV, mobile phones, and many of these very useful technological tools that we use, all are outcomes of this tremendous revolution that Maxwell initiated.
Now, between Newton and Maxwell, scientists thought they knew how the real world worked. Things orbited around each other, and pretty much everything that was transmitted, including light, came in waves, like the ones you see when drops strike water. We'll call these brilliant observations the classical world, a world where everything is predictable and looks familiar. Which brings us back to Max Planck, who launched us into the quantum age, the age of lasers, CDs, computers, and personal communication devices. He was studying something that was far removed from these futuristic devices. As I said earlier, he was trying to figure out the mystery of why objects changed color as they got hotter. Now, you might wonder why anyone would want to study something that's so, well, so...
We might say that this is a boring question, but for physicists it was very interesting.
And if Max Planck hadn't found this seemingly boring subject fascinating, we might not have quantum physics.
Just as Isaac Newton had used the laws of classical physics to describe the familiar world around him, Planck also wanted to use this approach to understand why objects changed color as they got hotter. But what he found was that the laws of classical physics weren't working. They gave the wrong answer. So he tried a whole new approach, a whole new mathematical hypothesis. And when he did that, it worked. He got the right answer. But the problem was, this new hypothesis didn't fit with the laws of classical physics.
Planck had provided an extremely accurate explanation, but he did not believe it himself. The first person to take Planck's idea serious was a young patent clerk at the Swiss Patent Office, Albert Einstein, whom nobody knew at that moment.
Einstein figured out something that Max Planck couldn't believe, that light is not just a continuous wave. Sometimes it behaves like a particle. Physicists call this wave-particle duality.
One of the greatest intellectual achievements of Albert Einstein, the one he got a Nobel Prize for, was to realize that light acts as if it came in pieces, in chunks, quanta. Quanta of light are called photons. The inkling of that came before in the work of Max Planck, but in his work it was just a mathematical artifice. Einstein realized it's just not mathematics, it's really physics. And he drew consequences and explained experiments which could not be explained with waves.
Einstein's work marked a major turning point in the development of modern physics. Then in 1913, Niels Bohr started filling in the quantum picture by explaining the structure of the atom using these simple equations. Okay, maybe not so simple if you don't speak math.
Bohr was able to explain the properties of atom using quantum mechanics. He used a model called a planetary model, which is similar to the Earth going around the sun, where, in the case of atom, it is the electron going around the nucleus.
But Bohr's math showed him that electrons didn't orbit the nucleus of an atom in quite the same way that planets orbit the sun. Instead, they could orbit the nucleus only at certain specific distances, something quantum physicists call discrete distances, or quantization.
And this was deeply unsettling to a generation of physicists who had been brought up on the notion that things change smoothly. For example, the way the moon circles the Earth and the Earth circles the sun.
But Bohr's postulation assumed that electrons behaved like particles. It took French physicist Louis de Broglie to show that atomic orbits can be explained by assuming that electrons, normally thought of as particles, can also behave like waves. But each of these postulations on their own didn't provide the entire picture, and the quantum conundrum had disconnected dots that went from Planck to Einstein to Bohr and then to de Broglie. What was needed was a theory to connect those dots and clarify how a wave could act like a particle and a particle could act like a wave, to explain the mystery of the wave-particle duality of light and matter. And in 1925, Erwin Schrödinger formulated the now famous equation that bears his name.
Schrödinger's equation really laid the foundation for what became a full theory of quantum mechanics. And this new theory not only gave scientists a universal recipe for understanding all of the previous quantum phenomena, but it also gave scientists a systematic way to explore the atomic world to find new quantum effects, unexpected ones. Ultimately, the quantum theory gave scientists what is probably the most accurate and most powerful theory ever devised by humanity.
While the discovery of quantum theory was enormously useful as a scientific tool and made many of our modern-day technologies possible, it actually raised more questions than it answered. Many of these questions are illustrated by the famous double-slit experiment, an experiment that, to this day, sets physicists' hearts aflutter.
The double-slit experiment is actually a metaphor for saying wave-particle duality. What does it mean? In classical physics, we have waves like sound waves or electromagnetic waves. And we have also particles like billiard balls. After quantum mechanics, a particle, like an electron, can also sometimes behave like a wave.
The double-slit experiment is so exciting to physicists and so interesting to everyone interested in quantum mechanics because it contains the essence of quantum mechanics.
In the double-slit experiment, a beam of electrons strikes a battle with two narrow parallel slits in it, and then a screen.
When we do this experiment with the lights on, nothing unusual happens. the electrons form the same pattern on the screen that you would expect for spitballs or wads of gum or even tomatoes. But when we turn the lights off, something very surprising happens.
What one observes on the screen is a series of maxima and minima.
This series of maxima and minima is known as an interference pattern.
Maxima are places where electrons accumulate. Minima are places that they avoid. The interference pattern is what you'd expect to see if you sent waves, not particles, through the double slit.
What we observe in the double slit experiment is explained mathematically by Schrödinger's wave equation, which predicts exactly the observed interference pattern. But quantum theory doesn't tell us where the particle is as it goes through the slits.
The essential difference between classical and quantum physics is that in classical physics one can predict both the positions and the velocities of particles, whereas in quantum theory one can't predict either.
Why is the pattern on the screen different, depending on whether the lights are on or off?
In classical physics, we are used to the universe which is independent of us knowing about it or not. We can look at it, but whatever it does doesn't change. It doesn't care. It runs according to its own rules. This is no longer the case in quantum mechanics. They're looking at something, making an observation of it, changes how it behaves.
But how can this be that in the quantum world, by just observing something, you can affect the way that it behaves? In our everyday experience, observation just means looking. It's a very passive thing to do. But remember, observation always requires light. And in the quantum world, light comes in chunks called photons. To see this, let's turn the theater lights back on and see exactly what scientists mean when they use the words observation and measurement. So in order to observe how the electrons pass through the two slits, you have to shine light on them. But when you do this, the photons can cause the electrons to behave differently. In this case, the photons make the electrons behave like particles. And so the interference pattern at the screen goes away. So now that we see what's happening when the lights are on, the question is, what's really going on when the lights are off? On this question, scientists have diverging opinions and some mind-bending speculation.
The double slit experiment shows that as long